So we'll be looking into what are the different, actually industry growth drivers, which has been really useful for, pushing the entire semiconductor industry. So we'll be first looking into that and then going on to the on-chip interconnects, what they are actually, why they are required, and why they have become so important. And then we'll try to look into, from historical perspective, that how interconnects have developed over the time, especially when we talk about these interconnects, how they have moved from aluminum to copper, and then looking forward for different other materials as well. So as of now, the efficacy of all these, optical interconnects have been already determined, but there are of course certain challenges that we'll be looking into. And therefore, what we say is interconnects are at crossroad. There are different other options which are available to replace the metal interconnects in the chip. So we'll be looking from from an point of view that how optical interconnects would be the possible solution, and then moving on, we'll be looking into the 3D integrated circuits that we can come up with these optical interconnects, and of course the challenges which are there with these optical interconnects to look into. Now going further, this is something which lays down the foundation, why and how the semiconductor industry has been moving on. Now, if you see from historical perspectives, on the y-axis, I'm showing you the business that is there in USD with different, different kind of applications. So things, if you see from 1985 to 1990, it was mainframes, which was, driving the entire semiconductor industry. Then from 1990 to 95, your personal computer era came into picture. And from 2000, 2000 to 2005, it was cell phone, which was actually driving the entire industry. The whole industry was focused towards, developing better and better cell phones. And therefore, the technology nodes were also being developed a lot, so that you do bring a lot of functionalities within these cell phones. And then from 2010, it was smartphone and tablets that was pushing the entire industry. It did not stop at that point of time. Actually, now the things that you see often is Internet of Things, which are actually driving the entire industry, wherein you're trying to make all the edges as intelligent as possible. You're trying to put up all those functionalities on the edges itself. So, the smartphone, which was there, had actually created the market for all these connected devices as well. Now, the important takeaway is, why and how all these devices have been so successful. And actually, how we're going to put up all these devices in a connection with each other through internet, that they make up a really good system altogether. Now, if you see from history itself again, the key trends at one of the biggest shows, which was, Mobile World Congress in 2014. So the observations that were made out at that point of time was that there will be connected cars, you'll have some 4G wearable devices, right? You will be having some Pebble steel watches that interface to start your smartphones. Then we went on with LG Lifeband fitness tracking and with heart rate earphones. So all these things were actually being discussed at that point of time. And if you see, these things have been already realized. And that is where, the potential of all these systems had actually increased a lot. So it's all mobility plus Internet of Things that has really made out everything so wonderful in this entire world. And it's good to see, but then your entire semiconductor industry is pushed towards putting up more and more functionalities on a chip. Now, while dealing with all these kind of systems, the important thing to note is the amount of data that you have to handle. and the amount of, the kind of systems that you need to come up with. Now, the number of RFID tags that will be embedded into our world and across entire ecosystems by 2013 at that amount of time was something like 5.9 billion, and this has actually increased a lot. Then further on, number of connected devices in the world constituting an Internet of Things, you expect 30 billion in 2020, and that is where we are actually. And of course, there would be, an estimate that was given at that point of time was that we'll be having something like 6.8 billion number of mobile phone subscribers worldwide, and we are touching that very closely. And the data that we are going to handle is something like 1.5 exabytes per month. So this has increased almost 2 times, every year, right? So the global mobile data traffic in 2013 was 2 times that of your 2012. So you can see how things had been, going up almost 12 times of 2000, and you could of course expect something like 16 exabyte per month by 2018, and that has gone even beyond that. So the things that were expected in 2014 really went ahead, and 2.7 billions, of course, would be the number of people on the internet in 2013, right? So all these things had really happened and going even beyond that. Now, when you put up so much of data all together, you need to see that the systems that you're working with is really good enough to support these kind of data handling, right? And how that has been made possible, and what are the different opportunities for IoTs, that had been looked into. So of course, there are different levels of, IoT kind of systems that we need to have and the applications that we are coming across. So if you see right from the bottom, level 1, wherein you have things such as baby monitors, home automation devices, drivers, your vending machines, trash cans, these are just level 1. Now, as you move up, for different levels, you do require, a lot of connectivity between them, and therefore your communications, cellular, mesh, Wi-Fi, Zigbee, all these things come into picture. And then as you move up, you have your computing and storages, where you do require energy efficient data centers, servers, routers, switches, storages accordingly. Then if you go further up the level, you have different apps that you need to consider in, right? So those apps, of course, are going to take up into consideration all these kind of stuff that you're seeing on the bottom. Now going further up, as you go up to the level 5, the consumers do require, support of big data, all those, analytics that you have to run as on date, So as of date, you do talk a lot about artificial intelligence, putting big data into, use and finding out the trends of, different customers. So all these things, business analytics or analytics, whatever you are looking into the different customers, that do require a lot of processing also. And of course, that has to run on certain machines which need to support, these kind of processing power and storages as well. Now the market actually has really grew a lot from something like $35 billion to $200 billion by 2020, and that is still going up. Now by 2017, it was expected that 50% of IoT solutions will originate in startups less than 3 years old. So this is how the startups, and that's true also. If you see from Indian perspective also through the entire world, most of the startups which are coming up in, especially in this business analytics, have been doing really nice. They have been, putting up a lot of data for, major companies to understand the trends of different users, different products, so on and so forth. Right, so all these things, when you look into, as an economical, up economically, if you go up, you need to look into all these applications, but that has to be supported by certain semiconductor technology, right? And when you look into all those chips that you have to come up with, the amount of data that you have to entertain, right? So all these things, when you look into, you have certain, parameters that you need to look into, especially power consumption, security, footprints, right? So all these things have to be looked into. And of course, the applications are not just what I have been talking about in the previous slide, but there are, huge number of applications that require, humongous data to be handled. And among them, you have your smarter grids, wearables, smart home and building, smart cities, smart manufacturing for different industries. Then, of course, healthcare is something which is really looking up a lot of data into. Then your smart automotive also. When you look into all these kind of applications, right, especially these kind of systems, you do require a lot of heterogeneous integration. You do require a lot of heterogeneous components wherein contents not only from optical but spintronics, but for different materials, right, such as graphene nanoribbons, carbon nanotubes. Everything has to be brought out onto a single system. And of course, you do require your different integration, where you do look into different fabless startups where they propose different kind of designs without really coming up with fab. Other than this, you come up with these kind of systems where you put up on a single SoC, you put up memories, ASICs, your power modules, your sensors, RF modules, analog systems. All those things have to be put out on a single heterogeneous chip. And then you put up all these integrated fabless manufacturing, right, into these kind of systems. And of course, you have to look into all these foundries, equipments, materials, metrology, and testing as well. Now, when you go for your system level flexibility and reuse in integrating, multiple technologies, wherein you do work with, different process nodes and IP to bring thousands of new products to market, and that too, coming up rapidly and, quite cheap products that you have to come up with. So all these things, as far as international technology roadmap of semiconductors do suggest that you need to come up with these kind of systems that is able to, handle heterogeneous kind of components and integration as well. Now, when you come up with these kind of systems, where you have huge number of modules, all these modules have to be connected together, right, within a chip. Now, as I mentioned in the previous slide, you had different kind of memories, different RF components, analog components. Those are the different modules, and each of these modules have to be connected together, and they are connected together using different interconnects, right? Similar to what you see on a PCB board, right? Printed circuit boards. You had different, copper lines that connect either different components or different cells, different macro cells, or even going ahead with different PCBs to different PCBs. So that is what we call it as multi-chip modules also. Maybe MCBs and other things that you need to come up with, connect them together. Now they are connected actually using different different metals. As on date, we are using often only copper interconnects, but if you look into the previous 20 years trend, it was aluminum that was being used previously. But of course, we'll come down to why that was replaced. But let us see into interconnects. What are these interconnects? And these interconnects themselves pose a lot of challenges in terms of capacitive parasitics, your resistive parasitics, and as on date, it's having a lot of inductive parasitics also into picture. Now, these interconnects do affect propagation delay performance they do reduce reliability due to increase in noise. This noise can be either, crosstalk noise, or it can be, some other kind of noise also coming into these interconnects. Now, once we look into all these kind of, noises and propagation delay, you do consider the other performance parameters, which is, power dissipation also. So this power dissipation also is one of the prominent parameters associated with your interconnect. Now, when you look into all these three important parameters, of course, there are, some subsidiary parameters also, such as your area and other effects also, which I'll be discussing later on. But as of now, the primary parameters that you need to look into with these interconnects is your delay, reliability, and your power dissipation. So as far as different studies have been conducted, it has been observed that most of the chips that you manufacture fail out because of interconnects. It's all, the interconnects which has been really becoming a big threat for, coming up with better and better devices. Now, the interconnects classification, if you now look into the interconnects, as I said, in one word, they connect different macrocells, but these interconnects can have different length also. In interconnect which is connecting to different devices within a chip, that might be very small. Then when you talk about the other ones which are connecting, to different cells or maybe to different modules, their length would be much more larger. And accordingly, based on their length, they can be classified as either, semi-global interconnects or the global interconnects, which has, quite long length associated with them. Now, most of the focus towards development is towards the global interconnects, right? So the major threat that is posed is by global interconnects, and then your semi-global, and of course your local interconnects are really not that much, threatening. Reason being that their length is small, so they do not have too much of delay associated with it, and also the power dissipation is also not that big with them. But the global interconnects, which are running, for several, I can say centimeter within a chip. If the chip is something like 2 centimeter by 2 centimeter, the interconnect length, if you put together, if you just open up all those interconnects and join them together, that length can run into kilometers. So you might be wondering, how the length can become kilometer, but that's true. Reason being that you have something like 15 levels of metal interconnects within a chip. This is where you can see. So this is one, typical cross-sectional view for a chip, where you see on the bottom you have all those silicon, and as you move up you have all those metals, different metal layers. So you have two layers of your local interconnects, which are connecting to different transistors within this area. As you move up, you have your intermediate, which is something like 4 levels, and as you go up, you have global interconnects, and this cross-sectional view itself gives you a lot of information related to how these things are going to be connected with different modules. Now, if you see over here, as you move up, the cross-sectional or the thickness of all these interconnects is also increasing, right? So this is a cross-sectional view that you're seeing, but if you see into the board, the length of these interconnects is also going to increase a lot. And there might be, one question coming to your mind: why are we going to increase the thickness and the width of these interconnects? So you can assume that these interconnects have their thickness, and their not only their thickness but also their width is also increasing. Why? The reason behind that is, as you move up, your resistive effects have to be countered a lot because the length is too long. So if the length is too long, you'll always try to keep the cross-sectional areas to be larger enough so that the resistance levels are brought down. If it is not done that way, you can assume, you can understand the resistance that the signal would be encountering. And that resistance, if it is high, that would result in higher RC delays. And that RC delay you'll always try to keep as low as possible. Now, if you dig deeper into other perspectives, you'll find out that these, if you keep on increasing the width also, what you see is the capacitive effects is also going to increase, right? So that is one thing that people often ask, right? Now this capacitive effects, even though it's increasing, because you have all these dielectrics in between. I think you can understand that this, the green region that you're seeing is all dielectric, silicon dioxide or silicon nitride, so on and so forth. Now, once you have these kind of field oxide in between, the capacitive effect between the two interconnects can also increase, right? But to be honest, we do take up a lot of architectural change in these interconnects also, so that we can counter this crosstalk between two different lines because of the capacitive effect that is generated because of the dielectric which is put into between these two layers. Right, so anyway, what we try to do is we try to keep the resistive effects as low as possible, and the capacitive effects, can be countered by architectural change. So I'll show those, those structures also by which you can keep the capacitive effects as low as possible. Now, the next thing that comes to your mind is, how these interconnects is really affecting the entire performance. Now, those who are familiar with only devices, they might be wondering that no, it is the delay which is already going down, the power dissipation is going down, right, with better and better devices, technology nodes going from 180 nanometer to something like 3 nanometer. So I was just delivering one talk yesterday at Tampa Bay, and we were talking about the kind of devices which are going to come up. So the trend had been that we had been using planar transistors up to something like 2014 most of the time. Then in 2014, Intel came up with FinFETs. Then FinFETs, were even changed. We went on with the gate-all-around transistors. Then we went ahead with the nanosheets as on date. So already we have 5 nanometer technology node available with Apple A1. And now what would be the next? The next would be nanosheets, which will be coming up with 3 nanometer technology nodes. But of course, all these devices are becoming better and better. But ultimately, we have to connect all these devices. And these devices, although being very small, whether they do have enough drive current to drive these interconnects, or whether they are really good enough to drive other devices also. I mean, the fan out of these devices. That's really very poor from that point of view. It's really not good enough to have transistors that are not able to drive any interconnect. Now, reason being that these interconnects, they themselves have huge parasitics associated with them. Now, this slide actually gives you a fair comparison between the delays of different futuristic chips in comparison to the current one. Now, if you see on the left side, you have 4 modules available, and on the right side you have something like 16 modules available. And that is the trend actually. You're continuously increasing the number of modules within a chip so as to bring more and more functionalities. If you try to assume, you just try to look into history of mobile phones maybe 20 years back, I can very well recall in 2003 we used to have mobile phones that were really good enough for only talking. They did not have any feature, but then more and more features had been added. You had calculators, you had browsers, web browsers, and now you have huge number of things available within these mobile phones. And that is where the number of modules you are going to increase. You are going to pack up more and more transistors onto it. Now, if you see, the futuristic kind of chip and the previous chips that we used to have, they're all connected with global lines anyway. You have these global interconnects running. You have this semi-global one running in between, and then you have the local ones right over here. So the local ones, which has been shown very small in size, they just connect two devices, and their length anyway is quite small. The semi-global is something bigger than that, and then you have the global ones, which has even longer lengths. Now, what you see is, although the transistor dimensions have gone down, right, but then the global interconnect length has gone up. It has gone up by huge margins. So although the die size, we are not increasing much. You can see the die size has increased just 1.2 times or 1.1 time only. It's not going that up. But of course, we are putting up more modules within this. Reason being, thanks to smaller and smaller transistors. Now, if you try to make a comparison between gate delay and the interconnect delay, that gives you, fair comparison, fair understanding about how these devices and interconnects have been behaving in this in a chip. Now when you talk about the wires whose length actually shrinks is the local ones, because transistors being smaller are coming they are coming closer to each other much and much, and that way the length of these interconnects are becoming smaller and smaller. Now keeping those things into mind, still your local wire delay is going up slowly with respect to your gate delay. It's not that fast, but it's of course becoming, your local wire delays is going up slowly and steadily with respect to your gate delays. Now when you come to semi-global interconnects, the situation is quite worse in comparison to what you see with your local interconnects, right? There the wires whose length actually remains about the same is the one we talk about, the semi-global ones. Their length is almost same. But then the delay with these interconnects is much, much higher than your gate delay. Right? Of course, because gates have become really fast. And these interconnects are not able to keep pace with that. Now, going further up, if you go into the global interconnect situation, the situation is really very bad. The wires whose length increases with scaling, is the global ones. So you can see the length has already gone up, and there actually you find out the length of these interconnects once they are long enough. The delay is also very big in comparison to your gate delays. So what you observe is all types of signal wires delays are deteriorating with respect to gate delay with scaling. So it's sort of a situation where the interconnects are really becoming very much worrisome for most of the industries. And therefore, it is the interconnect that determines the overall performance of a system instead of something else. Now, from historical perspective, you see, the feature size had been always reduced aggressively. That you would all agree with me, because that has been happening for a very long time, because you do gain a lot in terms of speed, in terms of power, in terms of silicon area, and of course the cost characteristics as well. And it was expected now that the feature size of several tens of nanometers would be available, and that's true. This is from a standpoint of view in maybe 5 years back or 10 years back. Now, we have something like 5 nanometer technology node, and of course the number of transistors within this chip would be something like billion in number. That's true. But the clock speed, which was predicted by ITR as something like 10 gigahertz, has actually not happened. Now, why this has not happened? If you try to see the trend, we went from 1 megahertz to 500 megahertz and also to 1 gigahertz very fast. Things developed a lot quickly. And then we went on to something like 2 gigahertz and 3 gigahertz quite slowly. Now, why did that happen? Why did the things went slow from 2 gigahertz to 3 gigahertz? Reason being that the power dissipation was going up, enormously. And when you're dealing with very high frequency, the interconnects themselves start posing, huge threat. Huge threat in terms of reliability. And therefore, it was really very difficult to go up beyond 3 gigahertz. Although ITRS had predicted something like 10 gigahertz, but that did not happen at all. Now, the reason behind I have already talked about. Now, how the things were really taken care of. How did we, really increase the performance still beyond that? The way people, found out was using more and more pipelining and more parallel processing. And therefore, we came up with, more number of cores, multi-core kind of, processors. And as on date, we do have processors which has scaled up something up to, 128, 256. And within, short span of time, we'll have processors that will be having, something like 1,000 cores, 2,000 cores. So we have not, actually in total, what we have done is we have not increased the clock frequency, but of course we have increased the number of cores so that we could, still match up with the requirements of the customers and the industry as on date. Right, so, but of course, distributing robust and reliable signals through all these interconnects in such a high speed, high complexity environment is really a challenging task. So as on date, it's really difficult to, distribute this power and ground lines, clock lines, data and address lines, and other control signals that runs through all of these cores within a chip. So that is where the challenge lies, right? And already we are into nanometer regime. The designers are scaling down the global wire dimensions more slowly than the transistor dimensions. And there's a huge rapid growth in the gap between transistor density and the interconnect density on a chip. And of course, we have to use these global interconnect resources, more optimally. They are really, valuable resources as on date. And what you see is the interconnects rather than device determines the chip performance. It's really these devices, interconnects, which are going to determine the overall performance of any chip. Now, going further into this, if you see the trends, how the things have been really moving up. So the node dimensions is on the y-axis, the bump pitch is on the right axis, and what we're trying to see is the silicon scaling versus the packaging scaling, right? So the chip packages, how they're going to be scaled, right? That is what we are trying to see. And if you try to see over here, the trend, the minimum chip feature size has really gone down. It has been going down and it's down further on. So we are already into 5 nanometer regime, as I told. So this is something where we have captured up to something like 2018-19, and this is really going up fastly. But the other thing that you need to look into the chip package interconnect, right? That has really not gone down drastically. It's still, it's leveling off. It's almost at the same stage. Did some changes over here, but never matched up with the minimum chip feature size. This is something which is very interesting. So packaging has not scaled much compared to the silicon in last 40 years, and this is what we expect further on also. Now scaling the package and the board will be central for the next decade. This is what you have to do. You have to scale down it. But then why this scaling is not possible? Because as I told, if you scale down the dimensions of these interconnects, you're going to land up in another problem of higher delays, because the resistive parasitics would become so high that you won't be able to transfer the signal from one end to another end in a chip itself. It would be taking huge delay time, and if the delay time is huge, the chip frequency has to be brought down, and that you won't agree anytime, right? So that is where the usual trend is. So there are a lot of challenges which are there for copper interconnects. So as on date, we are using copper interconnects itself. So in early 2000, it was realized that even copper is not able to fulfill the demands of high-speed interconnects. So before 2000, 1980s, 1990s, when we had all these kind of integrated circuits available, at that point of time it was aluminum that was being used, but then it was replaced and then by copper, and then later people found that even copper is not good enough. So with the increase in integration density of CMOS and higher clock frequencies, the requirement of lower resistance and higher bandwidth is one of the major concerns for these materials, especially the copper. And to accommodate more interconnects in a chip, the cross-sectional dimensions are being reduced rapidly, resulting in dimensions reaching in the order of MFPs of these electrons. So the MFP, mean free path of these electrons, is something like 40 nanometer in copper at room temperature. And once you are very close to MFPs, the things become really very difficult to handle, because you do come across a lot of scattering effects, right? You have a lot of enhanced grain effects. So all these things, starts coming into picture, and your resistivity of copper interconnects, still starts increasing even more rapidly. So that is where, you have to look into to find out the replacement for copper as well. So this is the trend that you're seeing, the copper resistivity trend. So as the line width is going down, your surface scattering and grain boundaries become prominent, and therefore, your resistivity starts increasing further up as you move down to smaller line widths. So resistivity increases as wire dimension grain size become comparable to the bulk mean free path of the electrons, and these effects becomes prominent. And once these effects become prominent, your power and power density is going to go up drastically. So this was something noted by Mark Horowitz very long time back, when they showed up that the power dissipation is rising to exorbitant proportions. Your power density is rising even more because your die area is no longer increasing. You're not going to increase the die area. Now the question that comes to your mind is, why do not we increase the die area? So it's a thumb rule that if you keep on increasing the die area, the number of failures would increase exponentially. The yield will go down below 10% or 5%, and which is really not acceptable by any industry. If the yield is too low, the cost of those chips, the good chips, would be distributed among the users who are going to use it, and that increase in the cost would be too much. And therefore, you need to come up with higher power and higher power densities going up, regularly over the years. You need to come up with novel schemes to reduce power dissipation in each department, right? And interconnects is something which is very important, right? So we have been able to handle devices very well, right? That is for sure. But the problems with the interconnects are still at very nascent stage. They are still, requiring huge developments. So the technology node, over the time, if you see, the dielectric constant has, moved down to reduce the problems of capacitances and the larger power dissipation. But still, the thermal problems are still coming up. It's becoming, the temperature is still going up higher and higher, and this is where, you are seeing that these metal lines are becoming, more and more hot. And once they dissipate so much of, heat, what happens is your higher temperature results in higher resistance, and that would result in lower reliability also. So that way, you need to look into these aspects, and therefore you do require better circuit design techniques needed to reduce power, better cooling techniques needed. So all these things are required. But anyway, what you see is that because of high temperatures, your electron migrations comes into picture, and you can see that this is one metal interconnect, and once you pass heavy current through this for a very long time, what will happen is the metal itself will get displaced. And once the metal get displaced, you'll have some hillocks and some voids that are created, and these hillock and voids are actually going to increase the mean time to failure. You can see over here, with every increase in 10 degrees centigrade, the mean time to failure will go down by 50%. So you'll have more failures. And of course, the performance is also affected drastically. As the temperature goes up, your resistance goes up, your RC delay also goes up, and with each 10-degree rise in temperature, your speed will go down by 5%. So this is what I'm talking about within a chip, right? Not the ambient temperature or the climatic temperature. People do confuse with those aspects. The chips are much, much hotter in comparison to your ambient temperature. So this is what the electromigration effects comes into picture when you talk about all these kind of systems. Now, once you understand that, yes, these are the threats, these are the problems that you come across with the interconnects that we have been talking about, the copper, which we are using as on date. So the researchers, started finding out the different ways by which you can have better interconnects. Now, if you see the interconnect technologies, this is something, the crossroad where people have been looking into different options. If you see, the copper, is being thought of to be replaced, and what are the different options that we have? So what you see is the optical interconnects is one of the options where, the lasers, modulators, detectors, all these WDM components have to be, developed and used. Then your nanoscale photonics and plasmonics is another option where we are looking for different kind of photonics based interconnects or plasmonics based interconnects. Then of course you need to have some silicon compatible photonics that can be developed, and then you have different other ways also. People consider spintronics based interconnects also, but over the time that has not really taken up or did not move further because the relaxation time, right, was not that high for these spin-based interconnects, and therefore it was observed that they are good enough for only local or semi-global, not for the global ones. The other prominent material level kind of stuff people looked into was nanotube interconnect. This is where it has been shown. So if you replace copper by carbon nanotubes or graphene nanoribbons, this is also considered as one of the good options. But of course, you have a lot of fabrication challenges associated with these nanotube interconnects. So people have thought of for different metal nanowires, silicon nanowires, and other silicon nitride or silicon nickel. All these kind of different, not silicon nitride, but silicon nickel kind of metal nanowires have been looked into, and that is also being worked after by different researchers. But the two prominent devices or two prominent technologies which people have been considering aggressively is either replace the copper by carbon nanotube or use optical interconnects, right? So although others are there, but they are still at very early stage. Their developments is not that much as in comparison to your optical interconnects. So as I mentioned, the alternative candidates are optics and carbon nanotube. This is what people have considered. And if you see the pros and cons for these two options, if you see for optics, it has low loss for longer wire and higher bandwidth. That is for sure. Then you have lower power at higher bandwidth and switching activity. And of course, you do a lot of WDM, wavelength division multiplexing in optics. That is really good for interconnects, especially on-chip interconnects, where you are able to carry more than two signals on the same optical fiber. But it's not only WDM, but people have gone up to deep WDM. So that is where actually the optical interconnects are really useful. Then the cons, if you see with these optical interconnects, is larger pitch. And of course, you have lower bandwidth density. That is something of concern, but that can be taken care of with this wavelength division multiplexing. This is something which is going to help us a lot. Other than this, which I have not mentioned here, is development of on-chip lasers and detectors. That is one of the concerns, and then heterogeneous integration of all these components on a chip. The other option, as I mentioned, is your carbon nanotube. They are smaller device, something like smaller in size, such as nanometer dimensions. Of course, they have very long mean free path that can go up to 5 micrometer, and that really helps in reducing the overall resistance also. But then power is something which is one of the major concerns. Apart from this, apart from power, you have other concerns, that is high resistance between metal and carbon nanotube. So of course you have to deal with different metals, and those contact resistances sometimes are very high, and therefore you do nullify whatever benefits that you have gained through carbon nanotubes. So as I mentioned in the beginning, the optics is creeping closer to the chip. So we were considering it to be only for long haul communications earlier, then to local area networks, backplanes, board to board, chip to chip, and now it has come down to within a chip itself. That is coming up quickly. Now, if you have a comparison of optical versus electrical wires, this is how it looks: the electrical interconnect, where you have a driver and a receiver, and between you have the repeaters for long interconnect, so that the delay could be reduced by it. And in fact, we have studied a lot about repeater incision for reducing crosstalk also. So that is where actually these electrical interconnects can be quite handy, and that is where it has been going up. And if you look into optical interconnects, you do require a transmitter system which has a laser source and a modulator. You have a driver in between, and then you have your receiver side, again a photodetector available. You have your different stages of CMOS based. So all this gray has been shown in CMOS, and then the all optical stuff has been shown in red color, right? So development of these photodetectors, lasers, and modulators is something which is challenging, and putting them onto a chip is another challenge. Now, what are the enabling technology or devices that can be really useful for putting up all these devices? So the enabling devices are your different kind of materials such as 3-5, right? So that can be integrated with your silicon CMOS. Then also we can look using germanium, which has really very good band gap of something like 1.5 micrometer, and this is really integrable on the silicon chip also. So the question is how to put up all these heterogeneous technologies. Now, when you come to types of optical interconnects, right? You have different types such as free space optical interconnects, substrate mode optical interconnects, thin film guided wave optical interconnects. So all these things have to be looked into. So the first thing that were proposed was free space optical interconnect, wherein you had a source, right, and a detector on the other side, and this optical signal propagated after getting it reflected on the other side. This is how it works. But the problem with this is is the 3D alignment between detectors and the signal beams and the high crosstalk levels that you come across. So this is alignment which is going to really kill these kind of free space optical interconnects for any usage in a chip. Then people came up with your substrate mode optical interconnects, right? So this is where we had a transmitter and then a receiver on the other end. The coupler, which is going to couple the light onto this, waveguide or substrate that you call, and this is how it, propagates and then again latches up with this receiver detector on the other side. So in this case, the light must be coupled from source into substrate and from substrate to detector. This is how the thing goes. Now, the challenge with these kind of substrate mode optical interconnects is that these interconnects require 2D alignment, but of course are better than your free space optical interconnect that we had talked about in the previous slide. And it does have some benefits in terms of reduction in crosstalk as well. But these optical interconnects cannot compensate for source divergence that comes up, and does require collimated optical source, which are really bulky and alignment sensitive. So if you see, the two interconnect types that we have talked about is going to have huge challenge because of their alignments. That is one thing. Then came up with your thin film guided wave optical interconnects, which people have looked into, where you have a source, right, which is coupled to an interconnect, which is almost a waveguide, very thin waveguide, and then you again have a coupler on the other side, and you have a detector onto that, right? So this is another trend. It does have a lot of improvements in terms that it requires only 2D alignment. They are quite robust and have low crosstalk also. But then it has few other things also that needs to be looked into, right? So it's sort of the thin film that you're going to come up with has to be really very precise, right? But altogether what you see is you have huge benefits. They have higher tolerance to source divergence, and they do allow for use of integrated optical devices such as direction couplers for routing and splitting the signal as well. So those were the interconnects that you could use, sort of waveguides, right? So developments have been really rapid in that area, but now the next biggest issue is coming up with laser source within the chip, right? It's not quite easy to couple or use a laser source out of the chip. Then you have to couple that light also, and it's not really that easy to come up with these laser sources from outside the chip and then making those alignments. So people have thought of using only on-chip laser sources also. And the one that comes to your mind, is vertical cavity VCSELs, vertical cavity surface emitting lasers. Now, these lasers are strong contender for future optical interconnect transmitting source. They are, of course, able to provide very low threshold current of something like sub-milliampere that can really take care of the power dissipations that would really come up with these VCSELs otherwise. But still, you have a lot of issues like threshold current stability, wavelength stability, and thermal limits that needs to be considered before you come up with large-scale use of these VCSELs within the chip. So this is how it looks like, where you have different Bragg reflectors, you have apertures in between, right? And then this is where you generate the light. So either it can be surface emitting, lasers or vertical cavity. So VCSELs are much more prominent and much more useful for chips to get integrated with them. Now this is one study that was conducted by Chen et al. Right, and this was a long time back when it was conducted, and that point of time, the optical and the electrical ones were compared in terms of delay, and it was observed that your electrical interconnects are going to have delays that will keep on increasing, right? So this will go up from 311, something like nanoseconds, to something 317. But of course, optical interconnects, as the technology node goes up, this will go down. This is what is expected. So therefore, optical interconnects, of course, would be quite useful put all together. When you talk about power dissipation of optical and copper interconnects, this is Kimmerling, that the group that conducted the entire study, and it was observed that the total optical interconnect this power dissipation would be quite small in comparison to what you'll see with your electrical interconnects. If you see with electrical interconnect, this is going up rapidly, although with optical interconnects also it is going up, but it's not that rapid and that high in comparison to what you see with your electrical interconnect. So that way, the optical would be the one choice that people would be looking into. And of course, with all these optical interconnects, the growth is going to be really very, very upcoming. Reason being that you do require a lot of systems that depend hugely on these kind of applications, such as Internet of Things, smart TVs, wearables. All these are the growth drivers that need to look into all these kind of heterogeneous integration. So we do have a lot of things onto this. We can have advanced node SoC die patterning with different different dies of different technology nodes, where we can have multi-die SoCs also, wherein different dies are connected through interposers, and beneath these interposers we have all those metal lines which connect these devices. So we'll be talking about 2.5D, 2D, 3D kind of systems here. Right, so all of these interposers do have through silicon interposers that connect different dies. This is what has been shown here. You have a silicon interposer and different metal lines which are connected in between, and that is where you connect different boards or different chips within this module. Going further, the ultimate things that we are trying to achieve is 3D stacking, right? So this is conventional systems that we talk of. Then we have 2.5D using TSI. This is what has been shown in a cross-sectional view. So we have all these kind of systems put together, right? So the 3D stacking is something which we are looking forward for, in the future VLSI chip, wherein all these modules would be stacked up, right? You'll have your CPUs, DRAMs, HBMs, all these things stacked up. This is where it has been shown here. You have your GPUs at 2 layers, then you have memory lines, modem, combo, RF, and on the top you have all those sensor nodes which has to actually interact with the real world. And with these kind of 3D stackings, you do require a lot of optical, routings to be done, because otherwise carrying such a huge number of signals using different lines would be really very much cumbersome. So that is where the optical chips or optical interconnects would be finding a lot of applications. Then you have this schematic illustration of fan-out WLPs, right? So different lines that you are going to get connected through your different dies. This is where you have a single die, this is where you have multiple dies, and this is where you see the cross-sectional view onto it. You have IC die 1, die 2 that has been connected using different routing layers which connect different ICs. Then you have system integration considerations that you need to look into. So the earlier trend that we used to have was, discrete dies on a PCB where we used to connect them. Then it went on to your 2D integrations that we often use where we have different multi-chip modules available, MCMs. Then we went on with your 2.5D integration where you have different CPUs and XPUs or your power units, then your caches, DRAM, silicon photonics all put together. In 2.5D integration where we have beneath this smart interposers that connect different modules, and then 3D stacking. So to be honest, 2.5D is something which has been really very successful. People have been working it with it. Right now also you do have chips which are 2.5D integrated, but 3D, is still far from, commercialization. Reason being that you need to, address to a lot of challenges which are there with, stacking them. Now, packaging solutions have moved on, right? So moved on to different trends. You can see the total die area size, how it has moved up. So earlier it was something like just 100 millimeter square with different applications, right? Now it has gone up to, the size has gone up further up, right? You have something like 400 to 600 millimeter square, and this is going up further up. Reason being that you're putting up more and more chip modules within that and using the different interposers. But this is what is required. Otherwise, you won't be able to match up the requirements that we have as on date. So these things have not only happened in your different application areas of maybe IoTs, but also this has happened for your smartphone requirements as well. This is how things have moved. So it's all similar things that has been happening over different application areas. This is again showing you different modules available and connected through different interposers in between, right? So you have different decaps that you have to reduce the interference and crosstalk in between. But of course you do have all these integrations that are going up, and that is being supported as on date by copper, but this has to be done with optical interconnects at 3D levels, right? So this is something which is putting up different application areas, showing how things are going to be connected together massively. So as we move up, you are moving towards big data faster at reduced power. This is what is something is expected. So you're going from 1.4 terabytes per second of HD movies per second that we need to handle, going up to 5 zettabytes, right? So this is something where you'll have 1.2 trillion high definition movies put together. You'll have requirements in terms of networking, memory, and then data centers, which has really become larger and larger, now putting up into clouds and enterprises, right? And the power consumption of all these data centers has been going up like anything. A country like Japan has been facing huge challenge, right? Huge challenge. Reason being that you can see over here, this is something, the mobile traffic growth which has happened in Japan. Why I'm talking about Japan? Because the power, that is being generated in Japan is not that high in comparison to what is being consumed by these internet users only, right? So if you see the power generation in 2007, if it remains same, that was something like 1,000 something like billion kilowatt hour. So if you see over here, it has been almost same. If it remains same, the power consumption, right, is going up, and in this power consumption, the data traffic power is something which is really considerable. So data traffic, I mean the internet users, the data centers, which are having all these memory and other things available, and that itself is consuming huge power, right? And this power would shoot up than what is being generated by 2030. So countries like US or India doesn't have that kind of problem, but smaller countries are really facing these challenges. So most of their power would be consumed by these internet users only, right? And that is something which is worrisome for them. And it's really very important that if you see that the thermal imaging of these data centers, the temperature is very high over there because the power consumption is too much, right? So the data centers alone would consume something like 7 gigawatt, right? Which is almost three times plus of what you do require with your Hoover dams. And therefore, it's very important that you do come up with green data centers. That means you need to look into silicon photonic solutions and the benefits that you expect using these photonic solutions that we have been talking about with using these optical interconnects. What will happen is you will replace the copper by this optical fiber network, and that will result in 79% reduction in power. You'll go from discrete optical to integrated silicon optical chips. You'll be putting up all those things onto a chip, and therein you'll see that discrete optical levels also you'll have 2 times your power savings. And when you talk about network on chip using all these silicon photonics integrated circuits with your TSVs through silicon vias and all those things, the power savings can go something like 2 into 10 to the power 3, 2000 times. So of course, the data centers have to look into all these solutions to reduce overall power dissipation. So there are different, trends that we need to follow. We need to come up with all these productization of these photonics packaging assemblies, wherein we need to have light couplings done more efficiently using either MEMS or different other technologies, where at least we do put up all these electronics and optics integration together on a 2.5T strategies, looking into all these aspects well. Otherwise, it would be really very difficult. So heterogeneous integration is something which is looked after aggressively, that brings out all these electrical and optical interconnects all together. So the local ones would be handled by these electrical ones, and the TSVs and other things would be taken care of by these optical interconnects. So the paradigm shift has been there, right? So you do have transistor scaling to system scaling, then Internet of Things, the next growth driver, and then you do look into fabless or foundry models. Integrated fabless manufacturing models have to come up, right? These are some of the technologies which people have been looking into, and so integrated fabless manufacturing is something which is call of the day. So people in countries like India that does not have too much of fabrication setup, they look into solutions through these measures, so that once they find out that it is good enough, they can actually make out all those fabricated chipsets. So this is how things have been moving, and this is my final slide that I want to discuss with you. So as of now, what you see is that chip scaling slows down. Your productivity will come from innovations at package level only. So it's packaging where the demand of all these optical interconnects would be huge, wherein you can put up, you can actually gain all in terms of power, delay, WDM, all these things would be quite useful. And the challenge with your IoTs, which do require a lot of integrations, right, where you do require a lot of sensors, memory, processors, intelligent nodes, doing all these edge computings, that do require a lot of integration, and that would be possible. If that is possible, you are able to bring out photonics solutions very well into that, putting up better and better technology trends, and that way you'll be gaining all together. And the things that you need to look into is the manufacturing supply chain, wherein the system integration based on multi-die packaging brings thousands of new products with widely varying volumes to the market rapidly and cheaply. So this is how you are going to move up in the technology trends, bringing optical interconnects into the chip, and not only onto the chips, but integrating these chips either in your 2.5D domain or your 3D. So putting up all those things together and harnessing the best of it, and coming up with power efficient solutions, and also speed wise also you do come up with better and better solutions. With this, we can conclude, and I'll be happy to take questions from the participants.
Thank you very much, sir, for your session based on latest technology used in industry. Participant, now we are at the end of the session. So if you have any query related to the topic, please discuss with sir. Participant, please, you may discuss if you have any query related to topic.
So Pushkar, just wanted to know how many candidates are there in this course?
Sir, currently 39 are present.
Okay, wonderful.
Right now, yeah. Participant, if you have any query, please.
No, I have no query, sir, but it was a wonderful lecture, sir. And sometimes I want to know about, sir, how to write effective DST proposal. Sir, this is the out of the area topic, but sir, I want your, expert opinion and expert suggestion for how to write a good effective DST proposal. Sometime later, sir, in a special session, you can.
Maybe once we are off the line, or maybe
Yes,
the recording is stopped, I'll be talking about it surely.
Yes, sir. Thank you so much.